Good afternoon, everyone. Thank you for joining us in the NOAA Central Library. This is Katie Rowley, Outreach and Reference Librarian, and I will be hosting the webinar today. We are very excited to have Andrew Hoell, who is a Presidential Early Career Awards for Scientists and Engineers winner, and he is from NOAA's Earth System Research Laboratory in Boulder, Colorado, working with the Physical Sciences Division. Andrew is going to be giving a talk today on guiding international food security assessments using subseasonal and seasonal predictions and predictability. Andrew researches the predictability of weather and climate at regional to continental scales, including assessments of individual extreme events like droughts and floods. He guides food security forecasts in Africa, Western Asia, and Central America based on lessons learned via research. And with that, I would like to tell everyone if they have a question for Andrew to please place that in the question panel, and we will be holding all questions until the end. And then I will be reading those off. If your question does not get answered, please know that Andrew will answer that offline, or we'll get back to you offline after the presentation. This presentation will be recorded and will be posted on the library's YouTube channel. So if you do miss it or you would like to share it after the fact with a colleague, you can find it there. And with that, I will turn it over to Andrew.
Thank you very much, Katie. It's my pleasure to be here and to talk about something that we work on very closely, which is food security assessments. If anybody has any questions and they don't feel comfortable asking them in the forum, you can send me a personal email at my email address, which is listed on this slide. So what I'm going to describe here today is how we guide international food security assessments within our lab here at the NOAA Earth System Research Laboratory, which is also a collaboration with our colleagues at the Climate Prediction Center and other agencies within the federal family, which include the USGS, NASA, and the USDA. We have a little bit of a unique perspective here because we're using our predictions and our predictability to help better guide and to make a more informed prediction as it relates to food security assessments. So there are really four main parts to what I'm going to discuss today. The first is establishing the need for famine early warning. And the second is how we interact with the Famine Early Warning Systems Network and what the Famine Early Warning Systems Network is all about and how they operate. I'll use the acronym FEWSNET. So FEWSNET stands for the Famine Early Warning Systems Network. The third part is really the FEWSNET approach, how they produce food security assessments using scenario development process and how we at NOAA fit into that scenario development process. And then in the last part, I'll talk about a case study about a scenario that we helped to develop for last year over Southern Africa, during which I'll highlight some of the research that we do and then how we use weather and climate forecasts to then help those scenarios. So really the marriage of the research of predictability science and also the interpretation of forecasts based upon that predictability research that we do. So I'll begin with the need for famine early warning here. So the need for food assistance is summarized in this slide that is produced by FEWSNET about twice a year. And it's really key because it summarizes a lot of the different regions and a lot of the different reasons for which these different countries have food security problems and need food assistance. There's a lot going on here, and I don't really have the time to appreciate it in full. But really the main takeaway here is these larger circles indicate that these countries have a more dire need for food assistance, insofar as that more people require this food assistance. Now you can focus in on a couple different countries, but what's really common among a lot of the countries that have food security problems are drought, economic shocks, and conflict. So really government, economic shocks, and weather and climate effects all commingling to produce food security problems. And at any given time, it could be all three, it could be one more than the other, and it's just a matter of a given year, a given season, a given situation. Take Yemen, for example. So Yemen is in a situation where they have the largest food security emergency in the world. And the reason for that is interruption in food imports. It says I'm experiencing technical difficulties. So Katie, if you see that, I don't know if you guys can hear me or not.
Yes, I noticed that it appeared that the audio and everything kind of shut off for a second, but I believe everything is back. If anyone has problems, though, please place those in the chat or the question panel, and I will try to address those. Thank you.
Thank you, Katie. So I was talking about Yemen and Yemen's food security problems. So really their main problem is imports. They can't get food in, and they can't grow enough to support their entire population. And on top of that, they have currency depreciation because of the economy there, and it's restricting food access. And Yemen is a difficult place, weather and climate-wise, because it's really an extreme weather and climate situation where you can get a lot of rain during one year, so help your crops, and then in another year you can get very little rain. And because of that, that introduces that shock to the system, in addition to sort of the background there as it relates to the economy and to the government. One thing that I really take away from this slide right here is in the lower left-hand corner, where FEWSNET discusses and shows the peak population in need of emergency assistance. So they go back some number of years to 2015 all the way into their forecast period or their scenario development outlook of 2020. And 88 million people within their purview are in need of emergency assistance. And this is a pretty staggering population given that the top 10 metro areas in the US only have about 86.8 million people. So the amount of people that FEWSNET is overseeing and trying to help right here eclipses and overshadows even the top 10 populated metro areas in the US. Now, what I'm going to discuss now is the Famine Early Warning Systems Network and what it's all about and how it operates. So really what FEWSNET is, and you can find this on their website, fews.net, it provides objective evidence-based analyses on acute food insecurity to help government decision makers and relief agencies plan for and respond to humanitarian crises. So that's FEWSNET really in a nutshell. So the map on the right here is a food security outlook provided by FEWSNET. This one happens to be for last year, so March to May of 2019, and this was made in December of 2018. What it does is it maps food security by administrative region according to the Integrated Acute Food Security Phase Classification version 3. For shorthand, we call this IPC3 classification. We don't use the long name. The key to that is acute. So acute in this context means that the level of food insecurity is transient. So the food insecurity classification here doesn't measure a chronic or persistent food insecurity. It's more transient and changeable. So the way the IPC classification works is it's measured on a scale of 1 to 5, where 1 is very little, minimal insecurity, and 5 is just a full-blown famine. IPC levels 2 and 3 are pretty common. They're pretty typical of these FEWSNET regions that we focus on. IPC level 4 is less common, and IPC level 5 is pretty uncommon. They really save that for the most dire of situations. And an example of that is the 2011 famine in East Africa. So on this slide, on this plot right here, they also show exclamation points. And what those exclamation points show is they suggest that food security would be at least one phase worse on the IPC scale if food assistance wasn't programmed. What that means is that they're trying to quantify exactly what the effect of this food assistance is for this IPC phase classification. So the reach of FEWSNET is pretty broad, and it's really across sub-Saharan Africa, Central America, and Haiti, and Afghanistan as well. So analysts sit in 22 field offices across the world, and they work with the U.S. government science agencies like NOAA, national government ministries, international agencies, NGOs, to produce the forward-looking reports that I showed, one of which I showed you before, for the world's most food insecure countries. So FEWSNET dates back to the mid-1980s. 1984 famines in Western and Eastern Africa really showed the need for food security outlooks and food assistance. So that's where FEWSNET was born and has been operating ever since in a variety of different manners. So this right here is the FEWSNET organizational structure. So what FEWSNET is it's a $900 million program within USAID, that's U.S. Agency for International Development. And FEWSNET will begin its 7th iteration come January 2020, so just a month from now. Right now we're in the 6th iteration, and this structure will change ever so slightly, but currently FEWSNET sits within USAID's Office for Food for Peace. And FEWSNET works with a lot of different partners. This is just a subset right here to whet your appetite. So the technical management for FEWSNET is controlled by a company called Schematic primarily, in collaboration for different aspects of the project with a company called Meteorologist. Then you have the federal science partners. You have NOAA, USGS, NASA, USDA, which handle the science behind this, whether it be monitoring the climate like the USGS and NASA tend to do, or producing the forecasts and making interpretations about prediction and predictability like we do here at NOAA. FEWSNET also works with external partners across the world, and they do that in order to produce robust analyses, to increase their data points, to work with folks, and those include the WFP and the FAO of the United Nations, so Food and Agricultural Organization. Now, what's key to food security here, and I kind of touched on this a few slides ago, are the factors that influence access to food. And in the broadest sense, they really fall under three umbrellas here. The first one is environmental, the second is social, and the third is governmental. Now, we talked about the governmental aspect before and how conflict and those situations help to affect food insecurity. The social aspect includes more of the economy of the region. So market prices, commodities and trade, income, market structure, how people interact with one another. That's within the government's purview, but not necessarily controlled by the government. And then finally, there's the environmental. What are the environmental conditions that are conducive to producing the crops that are necessary in order to feed populations? And if those crops aren't grown because of some reason or another, because of the environment, that's something that we really focus on here. So that's the role of the federal science partners, to monitor the current conditions, to get a handle of the subseasonal, seasonal, decadal variability, to be able to make and aid in those food security scenarios of the future by way of predictions and by way of doing a good job of monitoring the weather and the climate. Now, the next part of the talk is I want to discuss the FEWSNET approach. And the FEWSNET approach is something that is central to FEWSNET and how it operates. And what FEWSNET does is it uses a process called scenario development. Now, scenario development is widely used. And it's widely used because it produces a lot of structure into the analysis. Unfortunately, when it comes to food security and food insecurity, you can't forecast it with perfect accuracy. I mean, for someone who is very in tune with the weather and the climate, we have an appreciation for how difficult it can be to forecast whether it rains tomorrow or next week or next month or over the course of the next 3 months. Now, on top of that, you need to forecast food insecurity, which includes all the weather and climate information, plus these very difficult to forecast social, economic, and governmental factors. Key thing about scenario development, and I'll talk about this and how we build these scenarios, is it builds a structure and the logic into the outlook process, and it focuses attention on a subset of more likely outcomes. So keying in on those more likely outcomes is important because it narrows the focus and it allows for one to be able to get a good sense of what may happen in the future. Problem there is things do happen. Unforeseen things do happen, so there is some flexibility within the scenario development process in planning for the unforeseen. This picture right here is really a schematic of how one would use the scenario development process here. And this is how FEWSNET implements scenario development. So it's shown in the top of the schematic here. Future scenarios here in the left-hand box are used to classify future food insecurity, here shown in the center box, which then is in turn is used to advise the food security decision support here on the right. And again, that structure and logic that is built into the scenario development process, it allows for us to be able to focus on a subset of more likely outcomes instead of focusing on everything that could possibly happen, which would be really overwhelming and quite honestly probably impossible to do. It focuses here on the likely outcomes. Now here in the bottom panel of the schematic, the scenario development process relies on a number of key concepts, if you will. The first is the current conditions. What's the situation here? In terms of an environmental, weather and climate perspective, current conditions may include the soil moisture, or the soil moisture conditions conducive to the growing of crops. And then moving on, assumptions of future conditions. So given what we have right now, if we are to have a situation where we have above average rainfall or below average rainfall, or warm temperatures or cold temperatures, how will that then project into the future given the current conditions that we have right now? Then finally, the consideration of what those possible outcomes may be related to the assumptions that we have of future conditions and what we have currently. And then finally, here, even though scenario development does focus on the most likely outcomes, a consideration and appreciation for events that could possibly change the scenario. So you might ask, what is NOAA's role here? So what our role is we can guide scenario development by helping to produce robust assumptions about future weather and climate conditions on timescales of, a couple of days to a couple of weeks to as far as 8 months in the future. Obviously, it's easier, it's not as difficult to make good assumptions at shorter timescales just because we have a better handle on the weather and climate than we do at those longer time horizons, say 6, 7, 8 months in the future. And the way we do it is we provide our expert interpretation of the predictability and predictions of regional weather and climate. What can we expect? So for like Southern Africa or Eastern Africa, for example, how much rain can we expect? What kind of temperatures can we expect? How will that then translate into soil moisture? Will we have high soil moisture or low soil moisture? And how will that translate into crops? For an area like Afghanistan, where you have a very varied climate with a lot of topography, Afghanistan gets quite a bit of snow. So on top of trying to get a sense of what the precipitation during that wintertime rainy season might be, you're then trying to get a sense of what will the snowfall be? How much will it accumulate? How will it melt off? Will that melting then produce flooding, which then in turn would would hinder crop production or people's ability to go and till the fields or work in the fields, things like that. Now, the scenario development timeline that we abide by is generally about 8 months in the future. And it's really dictated how we produce those assumptions of future conditions that are then used to produce the scenarios by the precipitation and growing seasonal cycles. So this right here is for Zimbabwe, sort of in Central and Southern Africa. And this is Zimbabwe has actually a less complicated precipitation and growing seasonal cycle calendar, as you can see here on the screen. So Southern Africa and this area in Zimbabwe has a wintertime rainy season that generally begins in November and extends all the way through February into early March. So that's really when the time horizon for when we're looking at outlooks and scenarios begins. We're looking at November through the end of the rainy season. But we also have to consider what the distribution of rainfall might be. So for instance, planting in Zimbabwe tends to begin sometime in November and extend all the way through December and January, just based on the crops that are put into the ground. And it's really the distribution of rainfall that we see during this time of year that is key toward that planting process. So while we're looking ahead toward the end of the season, perhaps how much rainfall we may see, we also have to be mindful of the distribution of rainfall, at least during the time of planting and at the time of land preparation. And then as the rainy season ends and we then look forward into the future, the main harvest happens after that. And then beyond that, during the lean season and during the seasons when we don't have a lot going on agriculturally, people are then selling this agriculture on the open market. And this is when markets and trade become really key to the situation, because the environment here has done its thing, and now it's really the social effect that relates to food security. Now, this is the scenario development timeline that we tend to abide by here, and it's broken down into 4 parts. The first part is for 6 to 8 months before the start of a rainy season and the start of a planting season, if you will. What we're doing here is we're recognizing research on predictability of weather and climate. So as part of our duties and as part of our interaction with FEWSNET, we do research on how we can better predict and what are the predictors of regional weather and climate variability. And 6 to 8 months before the season, we're really appreciating that research and then trying to get a better sense of that in the context of what is to come. Now, 3 to 5 months before the season, what we tend to do is we incorporate seasonal to interannual climate modes relevant to region and current conditions. And by climate modes, what I mean is El Nino, La Nina, behaviors in Indian Ocean sea surface temperatures, maybe the Atlantic multi-decadal oscillation, maybe the Pacific decadal oscillation, factors like that, modes of variability like that, that may give us a better sense of how a season will behave over a given region. Now, within 3 months of the season, we begin to incorporate initialized forecasts. So forecasts from, say, the North American Multi-Model Ensemble, for example, we use very closely, very tightly within the FEWSNET outlook process, because they constitute the most forward-looking predictions of seasonal precipitation and temperature and variables that are relevant to agriculture. And then finally, during the season, we're monitoring the regional conditions. You know, what's the soil moisture doing? How's precipitation performing? What's the distribution of precipitation? How are the short-term predictions then sort of commingling and coming together with those long-term predictions? So really, the scenario development timeline that we abide by in order to produce assumptions and scenarios of weather and climate in the future, it's a hierarchy that starts well in advance of a given precipitation in a growing season. Now, in the final section here, what I'll do is I'll talk about how we produce scenarios based on this timeline using what research we do and the weather and climate forecasts that are available to us. And what I'll do is I'll take you through a case study of Southern Africa, precipitation during last year's summertime rainy season. So their summertime rainy season is nominally October to May. And during 2018-2019, October to May, Southern Africa had among the driest year on record over a large swath of the area. So that includes Botswana, Zimbabwe, southwestern Zambia, Namibia, Angola, southwestern South Africa. And you can see here on the right, this is how everything was in historical context. So again, this is among the driest, or if not the driest season on record. So it's a nice case study to revisit in how we handle the situation. So where I'll begin here is about 6 to 8 months before the season. What we're trying to do is we're trying to get a sense of, can we actually say something about a given season or a given region in terms of prediction and predictability. So this is an image from a paper that we had done actually this year. And what it shows is that for Southern Africa precipitation, the ability to predict, i.e. the predictability, varies very greatly from one year to the next. Some years simply aren't predictable. And the way to read this picture right here is that if you're closer to 1, that season was very predictable. And if you're closer to 0, that season was not predictable at all. So taking this predictability time series through time, you can see that some years just were simply not predictable, such as 1972. And by contrast, the following year, 1973, was actually very predictable. So it's important to appreciate this here, especially in the context of if we're able to say something about a given rainy season's performance, because some years we just don't have any ability to do that, and other years we do. Now, 3 to 5 months before the season, what we're trying to do is we're trying to incorporate some information about facets like El Nino and La Nina, because El Nino and La Nina really constitute the baseline for predictability and predictions over regions that we focus on, like Southern Africa. So highlighted here is another paper, and in this paper what we did is we aggregated a lot of precipitation data, and what we did is we asked the question, all right, how does El Nino and La Nina then change the distribution of Southern Africa precipitation? And it's pretty clear from this picture right here that during an El Nino, there's a shift in that precipitation distribution to dry conditions, while recognizing that, yeah, there is still a variety of outcomes that can happen. There is a higher likelihood of below average precipitation during El Nino. And by contrast, during La Nina, there's a higher likelihood of above average precipitation. So this is good right here. So what we know here is that, all right, some years simply aren't predictable, some years are, and that El Nino and La Nina, at least at these lead times, they constitute a very important aspect of the predictability and the prediction for Southern Africa. And here's another picture. And what this picture shows here is the precipitation day difference during El Nino and La Nina separated by month of the rainy season over Southern Africa. And what it shows is that, yeah, you know, on the whole, for an entire season, November to April, you're going to see below average precipitation regionally. But this is key right here because it actually maps out where you can see the differences in precipitation days. So, all right, in our inventory here, we have a knowledge of, okay, some years are predictable, some years aren't, that El Nino and La Nina constitute an important part of the predictability, and El Nino and La Nina, among drying during El Nino and wetting during La Nina, they change the number of precipitation days that happen over the region. So, okay, that's great. Now, we're within 3 months of the season. We want to incorporate initialized forecasts and say, all right, what can these initialized forecasts then help to tell us about how precipitation will behave over Southern Africa? So these are forecasts from November of last year, so November of 2018, for December 2018 to February of 2019. And what we saw during that time in the forecast was that El Nino was the favored outcome. So this right here, these sea surface temperature anomalies over the Pacific Ocean are consistent with an El Nino forecast during December, January, and February of 2019. And over Southern Africa, the forecast related to the El Nino was for below average precipitation to the west and to the east in the region. And the way to read this picture right here is to say, all right, these are the likelihoods of below normal and above average precipitation. And you can see that these warm shaded colors are preferring below average precipitation during the region. And now finally, okay, so we have baseline evidence for how predictable the region is and what the predictors are in terms of El Nino, and that we have an El Nino event. Now we start monitoring during the season and see the seasonal evolution of precipitation and of soil moisture and of temperatures. Now I'm showing precipitation here because I'm just showing a case study and something that can be easily communicated. And then going back to the slide that I showed previously, what actually happened during this year was that we saw well below average precipitation during in the region during that season, and it was among the driest on record. And below average precipitation is consistent with what we see during El Nino events. So as it relates to this scenario development process and for this region in this season, it actually turned out very well in the sense that we were able to give good guidance based upon the research that we had done about learning more about the region and how we can predict it, and also the initialized forecast systems that produce that forecast below average precipitation. So this right here is the final slide. It is again the outline, and I'll summarize with this. So what we do at NOAA and in our lab here in Earth System Research Laboratory, and in collaboration with our colleagues at the Climate Prediction Center, we help to aid the Famine Early Warning Systems Network by helping to produce food security outlooks using scenarios of weather and climate here. And we do so by applying our research on the predictability of regional climate and weather and climate forecasts. So that's where I'll end there. Thank you all for listening, and Katie, I hope I didn't cut out.
No, you were fine. I don't know what the glitch was earlier, but yes, if anyone does have questions, please place them in the question panel. We do have one question from earlier on in the talk from Elizabeth Lakeview. She says, when you say conflict is a factor, do you mean that political instability is a factor for food insecurity?
Yes, yes. Political instability is huge. That is, at least broadly speaking, it can be within the conflict framework, but any sort of political instability. If political instability is creating conflict, or if political instability is creating a situation where the economics of the region are really bad. So for an example, in Yemen, the political instability is helping to prevent a lot of those food aid from coming in and being able to help those people within the region. The political instability is also causing for currency depreciation. So people who once had $5 now can't go out and buy what they could buy before. So yes, political instability is very wide-ranging and has a huge effect.
In conjunction with that question, she asks, in those instances where there is a drought and political instability, how can you help in areas like that? How does NOAA help?
Well, NOAA helps by making when we can, making a good forecast. So the whole concept of early warning here is to be able to, you need to make a good forecast, and you need to be able to communicate that good forecast. And then you need to mobilize resources to help an affected region. So the best thing that we can do, and oftentimes we can't do it just because of the way the chaotic behavior of weather and climate, is to just make a good forecast based upon our research of predictability and our predictions that come out of our models. Now, it's not to say if we were to make a perfect forecast every time that it would help, because there's only so much when it comes to a given region, that political conflict, if that's still ongoing and food assistance can't be mobilized because there's political conflict going on, you can make a perfect forecast every time, but it really wouldn't help you very much. So it's a little bit of this, it's a little bit of that, and there's just a lot of factors that are going
on. Okay, thank you. Currently, I am not seeing any other questions. But if someone does, I will refer you back to Andrew's first slide and his email that you can ask him on your own. And I want to thank everyone for tuning in. You have about a half an hour left in your day. We're going to let you go.
Well, thank you very much, Katie.
Okay. Thank you, everyone. Have a good day.